One thing is, you have asked I was asked last time to check if we can find a different time slot, because there was some collision with the waiting for something? I was asked to see if there is a possibility of changing the class, the Thursday class, moving it to a different location. Now again, I don't know what's going to happen with this coronavirus or not, but there are two possible slots. One is 10 to 12 on Sunday, and another one is on Tuesday. Now, how many of you, now I don't mind to shift the Thursday. We have lectures on Thursday, right, 12 to 2. It's partial lecture and partial tutorial, right? Right now we still have lectures, but we'll start having tutorials as well as of next week. I do not mind shifting it to either of these two. I have a slight preference for Sunday. Is there anybody here who has a clash on Sunday? No? Do you know if there are other people registered for this course? That's okay. Somebody who's not here is not here.
You know, you invented those hours? Or
no, I did not invent the hours. I asked the secretary to check out with all the students who are registered for this course.
Because I think that we talked about these hours exactly.
Well, that's the hours that the secretary came to me. So let me ask again. Does anybody here have any objection that we move the lectures from Thursday, 12 to 2, to Sunday, 10 to 12? So avoid clashes. Again, I do not know if they decide to cancel all the lectures to shift them to, online lectures or whatever. But as far as I'm concerned, right now we have lectures as usual. So, okay? So if it's fine, then as of next week, I'm going to do this shift. So that means that we'll have the lecture from Thursday being shifted to Sunday. So next week, we're going to see you right after the weekend, hopefully, if there will be no further announcements or news. Sunday is at 10 to 12, and then the second one will be, as usual, Wednesday at 4 to 6, right? That's what we have. 4 to 6. We'll make sure that one of those will serve as a tutorial in the long run. Right now, we still do not need that because we're not that far. Okay, so that means that I'm going to see you on Sunday, this coming Sunday. Now, if you see other people that are registered, I'll put an announcement, of course, on the course's webpage. But if you see somebody else who's registered to this course that is not here right now, you can tell them about the shift. Okay, also, again, we are kind of on a very small number of students. If there are less than 5 students, and in principle, we don't have, we cannot open this course. So talk to other colleagues if they're interested in joining. They can still do that. All right, so far for the technicalities, and now let's go to some science. So last time, we started to describe special relativity. We said that the experimental basis for that is the Michelson and Morley experiment, which showed that the speed of light is constant and independent on the velocity of the observer. That led us to define that means that for two different observers, if they look at the light crest, right, that start at some time t equal x equal y equals z equal to 0, after some time t, they will both agree. The first one will argue that the light crest is at x squared plus y squared plus z squared equals c squared t squared, and the second one will argue x prime squared plus y prime squared plus z prime squared equals c squared t prime squared. Both would agree on this thing which we call the interval. So we define the interval as the interval squared, as denoted by delta s squared minus c times delta t squared plus delta x squared plus delta y squared plus delta z squared. When I say delta, that means the difference between two different events that are, each one is specified by its time, x, y, and z. Time and space locations. So t1 and t2. And the interval is delta t, is just t2 minus t1, x2 minus x1, etc. Right? And this is conserved. Both observers will disagree on the location, on the time of each event, but they will agree that the interval is conserved. This is the basis of the special theory of relativity. Then we had a new notation, which is going to stay with us for the rest of the course. We said that since each event is defined by 4 parameters, 1 of time, 3 of space, we write it as a 4 vector with an upper index, x mu, such that x0 is ct, x1 is just x, x2 is just y, x3 is just z. And then we define a matrix which had 2 lower indices. We call it eta, the Greek letter eta, eta mu nu, which is a very simple matrix. Most of it is zeros except for the diagonal, and on the diagonal we have -1, +1, +1, and +1. Okay? That is a very important matrix, so important that it has a name. It's called a metric. And using this new notation, we wrote down this equation in a very compact form. We wrote down that delta s squared is just sum over mu and nu, goes from 0 to 3, each one of them, of eta mu nu, delta x mu, delta x nu. And to confuse you even further, right, this and this is identical. We said that when we see an equation that in the same side of the equation we have both an upper and lower index which are the same, then we understand that there is a summation over them. This is called the Einstein summation convention. So we don't really need to write this sum. So this is enough for us to write eta mu nu, delta x mu, delta x nu. When we see that, we understand that there is a summation here over the 2 indices, mu and nu. All right? And then we defined a Lorentz transformation as a transformation of from one coordinate system to the other that does one very important thing. It conserves this interval. I should just say as a side note that this matrix, the metric, is in very wide use in physics, but in particle physicists, for a reason which is still uncertain to me, actually it is certain, but let's forget it, it is the same one as defined here, but multiplied by a -1. So in particle physics, if you look at particle physics textbooks, you will see the same matrix, only plus 1 minus minus minus. Okay? As you can see, the interval will still be conserved, right? It's equal to 0. So it doesn't matter if you multiply or not. And then we said, in Lorentz transformation, we write it down as lambda with one upper index and one lower index, but the indices are not one on top of the other, but there is a diagonal here, right? So you can write down x mu prime is lambda mu prime nu x nu, right? There is a space here. It's not one on top of the other. This is a transformation from one coordinate system which we call x nu to another one which we call x mu prime. And in order for that transformation, again, there is a sum here, right, for 4 indices. In order for that transformation to be considered a legitimate Lorentz transformation, it must conserve the interval, and we showed that this puts a limit on this matrix lambda, which will be represented by a 4 by 4 matrix, obviously, as eta rho sigma is lambda mu prime rho lambda nu prime sigma eta mu prime nu prime. Any transformation or any matrix that fulfills this condition is a legitimate Lorentz transformation. And we saw that this is like a very, seemingly very abstract notation, right? We have 16 equations because rho and sigma goes from 0, 1 to 3, 0, 1 to 3. So 4 times 4, 16. Each element contains a summation over u prime and nu prime. So there are also 16 elements in each line here. So there are 256 total elements here, right? Which we need to solve. But when we do that, we found out that essentially the matrices will represent either a rotation, usual rotation that we know in 3D, or a rotation where one of the axes is the time, in which case they're called boosts. And we show that essentially what we get is the same thing as we get when you do the old notation that you learn in first or second year when you learn special relativity. Okay? Now, just to make sure, did you review your knowledge in special relativity as I asked you to do? Who did that? Raise your hand. Only one. Please do it. Don't. It's not worth it. Okay? Did you look over Otvosh's experiment? Do. Okay. Please do. Okay? Really do, but otherwise you get lost here pretty quickly. Then we spoke about time dilation, and we showed that, again, this very abstract notation gives us a phenomenon which we know we're familiar with, which is a time dilation. Namely, if I'm holding a clock, right, I'm seeing the clock ticks at a certain period, certain time between each tick. If you are seeing me moving, of course the clock is not moving with respect to me, it will tick slower, right, because I'm moving. And we show that. And we show the delta t prime, time dilation. Show that delta t prime is just gamma times delta t. Gamma is just 1 over square root of 1 minus beta squared, and beta is just v over c. Any questions before we proceed on? Yes, please.
I think that I don't understand what is proper time, because on one hand it looks to me like a simple thing, the time in the not moving frame of reference. But on the other hand, it got its special name, and why it's so proper, because I can...
Again, the proper time, you understand it properly. The proper time means this is the time as it meant to be. Since time is something which is relative, if you see me moving, then you see that my clock ticks more slowly. But my proper time is my time.
But we have two proper times.
No, we have one proper time.
Because, but the system that is moving, okay, will see the other system moving by its own perspective, right?
So if I make a measurement of your clock, what you tell me is the following. Let's say that I am an astronaut, and I'm going now at some, on a spaceship at some velocity which is close to the speed of light, right? You would see me moving, my clock moving slower, right? I say, okay, I'm going on a trip which will take me 1 week, and you say, oh, actually it takes you 1 month, maybe, okay? But then you can say, okay, but from my perspective, I am not moving, you're moving, so you get slower. This is the very, very famous twin paradox in special relativity, right? Which we will resolve when we speak about general relativity. You'll see that we'll resolve it. Okay? But the definition of a proper time is not changed. Proper time is the clock as when in the frame that is not moving. It's my clock.
But we need to decide which frame is not moving, because two of them can move.
Right now, as viewed, right now, for the definition of a proper time, this is the time as viewed from a reference frame that is not moving with respect to the clock. This is my time in my frame. It's your time in your frame. Each one has its own proper time.
So any property that is inside a non-moving frame is a proper property?
Yes.
Okay, proper
Yes.
mass, proper length.
Exactly. Okay? This is, let's say that I'm going on a trip, and I don't know, it's a very long trip, I go to another galaxy, right? But I'm supposed to live 100 years, right? My biological clock means that I will die after 100 years. After 100 years, I will die. Now, you may say that I may live 1,000 years, right? But for me, after 100 years, if my biological clock tells me that it's my time to die, I'll die. I won't live any longer than that. Okay? The twin paradox is a very famous paradox of special relativity, which is resolved when we'll speak about general relativity. But right now, we're still dealing with special relativity, so the paradox is still here. Okay? Any further questions? So we spoke about transformation of the coordinates from one coordinate system to the other, which makes sense because two observers, we said each one can define his or her own coordinate system. That's fine. But in physics, we deal not only with coordinates, we deal with other quantities of interest, such as velocity or acceleration or other quantities. So we need to talk about vectors in general. So what I want to do now is to generalize the discussion to a general discussion about vectors. Let's talk about vectors. Now this is a little bit tricky and a little bit confusing, so let's do it slower so that it will be clear to everybody. Maybe it's not so confusing if you think of it in the proper way. Right. Now I am stressing that I'm not going to do the full development of the entire mathematics behind vectors right now because we don't need it. I'll do partly now, and partially when we speak about general relativity, I'll continue on the discussion. Right now I do only partial of the discussion to start to get you familiarized with the concepts. Okay. So the first thing, of course, the space now is four-dimensional, right? We speak about the four-dimensional Minkowski space. And so vectors will be 4 components, right? As opposed to three-dimensional Euclidean space where we speak of 3 components. Now they have 4 components. So we call them 4 vectors, right? four-dimensional Minkowski space. So we say that we have four vectors. That's the technical term. Now we'll keep the terminology for vectors. We might speak of three vectors when we need to, but right now, when I speak about vectors in general, it always means a four vector. So a vector has four components: 0, 1, 2, 3. Right? Don't get confused. Now, we already set the four vector, right? X mu, the position. Right? This is a four vector. Four components: 0, 1, 2, 3. That's the first example of a four vector. Now, we saw that under a Lorentz transformation, right, the components of the four vectors transform like that. Right? So I'm going to use that to define a four vector. So it's going to be the definition. My definition of a four vector is going to be the following. Any quantity whose components transform or undergo the transformation V alpha, let's say, transform to V alpha prime, which is just lambda alpha prime beta, V beta, when the coordinate system is transformed in the same way, so x alpha goes to x alpha prime, which is just lambda alpha prime beta x beta, is called a four vector. But the true term is called contravariant four vector. It's called contravariant four vector. Okay, this is the technical term. I'll give you a small example that will help you to understand what I mean by contravariant. Contravariant means that the components transform the opposite way as to the basis vectors. Okay? So what does it mean? Let's say that I have like a simple 1D space, which I measure length in meters. So my basis vector will be 1 meter, and let's say that the size of this part is 2 meters, right? So I say that the component of the vector is 2. Now let's say that I want to measure, to change the basis. So it's not 1 meter, but 1 centimeter. So I shrank the basis by a factor of 100. Now, what are the components of the vector now? It's 200 centimeters, right? So the basis vector is shrunk, but the component of the vector has gone the opposite direction. That's why it's called a contravariant. And the important point to emphasize, right, when I change the basis, I change the components. But what happened to the vector itself? when I change the basis, right? When I say I made a transformation, right? So I changed the basis vectors, right? What happened to the vector itself as an entity? Nothing. That's right. The vector is an abstract object. It's not changed at all. The components of the vector change. So the way I describe the vector do change. But the vector itself is not changing at all. Okay? So this is the first thing to emphasize. The second thing to emphasize, that can be quite tricky if you're used to think of vectors as, you know, arrows, right? Normally we write a vector with an arrow. Right? This is a vector. So the thing is that a vector is associated to a single point in space, or in space-time here. Right? It is not, you know, in Euclidean space sometimes we think of vectors as taking us from one point to the other. But this is not the case. A vector is associated with a single point in space-time. Right? In Euclidean space you cannot see it, but when we speak of spaces that are not Euclidean, that are curved, then what is the meaning of taking us from one point to the other? Right? In Euclidean space we can think of vectors as something which can have a direction and a magnitude. Well, what is a direction if the space is curved? Okay? So let me write it down because this is really important, that a vector is associated with a single point. Leave that for a side. Each vector is located in a single point in space-time.
Is there a simple example in Euclidean space for covariant vector?
Yes, but you will not see it in Euclidean space. I'll give it to you. Yes, there is, but not now. You'll see it. You have to think a little bit careful about that. I'll give it to you down later on this lecture. Okay. That's the important thing. It's located in a single point. What does it mean? So if we think of a space, let's say now I'm going to emphasize a space which is not necessarily flat, right? Let's say a curved space. So let's say a curved two-dimensional space, right? Something like that. And I choose a point P on that space. So that space, by the way, the technical name is called a manifold. So I'm going to call it M. It's a manifold, right? And through that point P, right, I can associate a set of all possible vectors which are located at this point. Right, so let's draw it. This is a vector, this is a vector, right? They are all going to be associated with this point. And all of them, of course, form a space, which is known as the tangent space to the point. So all these vectors, they form a space, right? I took all the vectors that go through the point P, right? And they form a vector space. This is the tangent vector space to the point P, so I'm going to call it TP. Now, if the space is flat, right, if I move from one space to one point to another, I'll get the same space essentially, right? But if the space is not flat, like in my picture here, right, if I choose a different point Q, and I take all the vectors that go through the point Q, right, they will form a different space, TQ. It's not the same as P in general. So again, the way is that we take a point P on space-time and we think of all the vectors that pass through this point P. They form a space. This is a tangent space to the point P. I haven't gone through exact definition here.
No, I mean the tangent.
The tangent is an abstract vector space.
It's not flat in geometrical sense.
If I do a 2D non-flat space, curved space, think of the surface of a sphere, for example, right? Then it will be like a 2D, right? Yeah. But if it's a 1D, it will be a 1D, right? If it will be a 3D, it will be a 3D, right? It's a general, yeah. The correct way to think of it is it's an abstract vector space. Have the same dimension as the space itself, right? That I have. Just a few words of this thing which you call manifold. I haven't really defined it. I'll define it later on down the line. Remember when we spoke about non-Euclidean geometries in the introductory part of the course, right? I said that we're going to look at spaces which are not Euclidean globally, but locally they are Euclidean. So that's why I can do that. The spaces I'm going to deal with, they don't going to have any spikes or anything that mathematically behaves bad, right? So if I zoom in, locally Euclidean means that I can zoom in, and the more I zoom in, the more Euclidean-like they look like. Right? So they're well behaved in that sense. Okay? It's not a mathematical definition, but we're physicists here, we're not mathematicians, so I allow myself to be a little bit sloppy here. Okay? For us, the set of all vectors, the important thing for you to remember is that each vector is located in a single point in space-time. Right? When I say a vector is located at a single point. Now I look at the set of all vectors that are located at that point, P. Right? This is contrary to what you may know as vectors that are connecting 2 points in Euclidean space. So no, the vectors are located at that point. So now I'm looking at the set of all vectors that go through P. The set of all these vectors, they form a space, which is tangent to the space. That's why I call it the tangent space, TP. The tangent at that point P, right? You're right that I can envision it if I have a sphere. This would be just like taking a flat surface and putting it on the sphere at that point P, which is what is being done here. But the space doesn't have to be a sphere. It can be anything. Right? So the way I think of it, this is an abstract vector space. And as such, it contains everything you know, everything you learn from linear algebra about vector spaces. Right? So let me write it down. TP can be thought of, it's not can be thought of, it is an abstract vector space. That means that it contains everything you know from linear algebra about vector spaces. Very broadly speaking, if we have two vectors, if V and W are vectors, and A and B are scalars, and of course we have A plus B, V plus W, or just AV plus BV plus AW plus BW, right? there is a zero vector, right? There is an origin, so there exists a zero vector. So v plus 0 is just v. Etc., etc. But we don't really care. The important thing is to, we don't really care in the sense that just follow what you know from vector spaces, from linear algebra. Will work out here as well. Okay? There's nothing different in this abstract vector space than any other vector space that you know of. Okay, now let's look about the basis. So, the basis for vectors and the components. That's an important point. Okay, so we already did it without saying it, right? It's very useful to take any vector and decompose it into components relative to a given basis. Right? What is a basis? It's a set of vectors that linearly independent. Right? So a basis is a set of vectors that what? One, linearly independent, and two, is that enough? No. What else do we need from a basis?
Span the whole space.
Span the whole space, exactly. In the sense that every vector in the space can be written as a linear combination of these four vectors. Right? How many bases do we have for a vector space? Infinite number of bases, right? But the number of vectors in each basis is going to be the same. And we call this number, the dimension of the space, right? We have infinite number of bases, infinite number of bases, but the number of vectors in each basis is the same and is equal to the dimension of the space. So, how many vectors are we going to have for the basis here in the space that we care about? 4, of course. This is Minkowski space, right? Right. So let's look again at the tangent space TP. Okay. Now let's set a basis. A basis contains of 4 vectors, which I'm going to call them E, mu. Now, there is a very subtle notation here. I put mu under parentheses here, right? Mu is just ct, x, y, and z. Right here. Or if you want mu 0, 1, 2, 3. It will be a more mathematically well-defined language, right? So E1 will be along the x direction, etc. Now, for the notation here, here we have 4 different basis vectors. It's not the 4 components of the same vector, right? I wrote x mu. This is the mu component of the vector x. But here I have 4 different vectors. That's why I put the parentheses here. Right? 4 different vectors. This is the component, the mu component of the vector x. Right? There's some subtlety of notation here. Now, I said that any vector, general vector A, can be written as a linear combination of the basis vectors. So I can always write A, any vector. All right, it's just sum mu equals 0 to 3 of A mu, E mu. I don't really need the sum, right? So I can simply write it down as A mu, E mu. Again, this is the component of A in the basis E. This is the component of A in the basis E. And this is a basis vector. Yeah, it is a basis vector. It's a given basis vector, yeah.
So I still don't get it why E mu it's not the same as X mu in the way of 4 different. I have 4 different E's, right?
Yeah, but each E is a vector. Right, so you can think of E0 as 1, 0, 0, 0. Right? E1 is 1, 0, 1, 0, 0, etc. A is just a number, it's a component.
And how do I...
Wait. One step at a time. Now A mu is the component, since A is a vector. Then I know what is the transformation law of A mu. Right? It will transform according to what I've written previously. Okay, so the classical example is a tangent vector to a curve. What did I do here? Let's say we have some curve, right? Let's draw it again. So let's say we have some space-time, and we draw a curve that goes through space-time. So this is the space-time, right? And I'm going to draw a curve through space-time. This is the curve. Goes through space-time. Right? So, you know, the curve will be parameterized by some quantity, let's call it lambda. And I can put the coordinate, right, x mu of lambda. So the tangent vector, right, the tangent vector to the curve at x mu, let's say this is x mu, right? So the tangent vector to the curve, right, I call it v mu, it's just going to be dx mu over d lambda. Now, of course, the vector itself, right? This is just a component of the vector, right? In the x mu, right? In the direction. But the entire vector v, right, is just v mu e mu, which is not changed. Now, when I make a transformation of coordinates, lambda is not affected, but the coordinates are affected, right? Then lambda is not changed, x mu is changed, v mu, x mu is transformed under the Lorentz transformation, as we described earlier, and so v mu will be transformed in exactly the same way. So the components of v will transform in exactly the same way. You want to be clearer, you know, this would be, let's say, x1, and this will be x2. Sorry, yeah, that's fine. Okay, now we use that notation, so we can use Einstein's summation convention, right? We see the same index, upper and lower, so really sum over it. Okay? But we say that v mu will transform under a Lorentz transformation in a certain way. Right? V is fixed. That means that the representation of the basis vectors will have to transform in a different way under Lorentz transformation. Right? In fact, in the opposite way. Remember the example I gave you previously. I'm changing the scaling from meters to centimeters. Right? So in fact, this is going to transform in the opposite way as the component. That's the origin of the name contravariant vector. Right? So how do we do the transformation of the basis vectors? Well, I pretty much said it already. It's going to be the opposite. So the transformation law of the set of the basis vectors. So we wrote down V as V mu E mu, right? We said that V is not changed under Lorentz transformation, right? So in the different basis, I can write it down as V, let's say nu prime E nu prime. Right? It's the same vector in a different basis. But this is the component of the vector, v nu prime. So I know how the component of the vector transform, right? This is just lambda nu prime mu v mu, v nu prime. All right? I just transform v nu prime. But you know, this is generally true, regardless of what the components of v mu are. Right? So we can write down E mu is just lambda nu prime mu E mu prime. Okay, but this is the old basis, and this is the new basis. Yeah.
It doesn't matter that the lambda is the same form acting on a basis vector that...
When I write it like that, remember there is a summation here.
Yeah, no, that is the question.
Yeah?
One row above, you transform
V, the component. Yeah?
Yeah. You transform with lambda,
Yeah.
a vector that has an index, an upper index. But one line beneath that, you transform with lambda, a vector that has a lower index.
Anyway. I wrote down, that's why lambda has one upper index and one lower index, but just before that. Now think of lambda as a matrix. Right? It's a 4x4 matrix. Now, when I write it like that, I do it component by component. So when I do it component by component, I can change the order, I can switch, I can multiply components. So mathematically, what I do is completely legitimate, right? But here's the point that I want to stress. This is, I could write down, this is mathematically correct. Let's see about the physical meaning, you understand in a second. I wrote down the old basis in terms of the Lorentz transformation of the new basis. But what I want is to write down the new basis as the Lorentz transformation of the old basis. So what do I need to do? I need to multiply by the inverse Lorentz transformation. Right? But the inverse Lorentz transformation, what is it? It's by itself a Lorentz transformation. Okay? So hence I'm going to have another subtle notation. I'm going to change the upper and lower indices. This is, I guess that's what confused you. Right? I can write down lambda minus 1 of nu prime mu. I'm going to write it as lambda nu prime mu.
This point we acted with this type of lambda on vectors of upper index.
That's right.
Yeah.
But that's why I have here an upper index. It's quite confusing, but yeah, this will be the inverse. Right? The upper index minus 1 would be. Okay? So what I'm going to do now, right? I can multiply by lambda minus 1, right? And then I get at E nu prime, which is lambda nu prime mu, E mu. Now that makes sense to you?
Yeah, that's what I was expecting before you.
Well, but the emphasis here, I needed to emphasize the fact that when I look at the set of the basis vectors, they transform in the opposite way to the components of the vector. Again, I'm emphasizing that, but when you think of it, it could be quite confusing when you think of the mathematics, but when you think of it in in the terms of this simple example that I gave, you're changing the scale from meters to centimeters, so you're shrinking the basis vector, but the components increase. Then it makes perfect sense. I just transform by the inverse transformation. That's all I want to say. Now, of course, I can write down that in terms of delta functions, right? So I can write down lambda, nu prime, mu, lambda, sigma prime mu. What is that going to be? It's the delta of nu prime, sigma prime. By the way, with the delta, I can write the indices one on top of each other. I'm not doing it. I cannot do it with the lambda matrices, but with the delta, this is just a delta function. Right, or similarly, lambda nu prime mu, lambda nu prime rho. What is that? Come on. Delta of what?
Mu
Rho mu. Okay. This is simply the traditional Kronecker delta symbol, of course, in 4 dimensions.
And can I switch the order of the indices of the lambdas?
No. You're not switching orders. H1 has a meaning. If you're switching orders, going up and down.
I mean, changing the levels.
No, that means a minus. If you're up and down, that means that you're looking at the inverse transformation.
Even if I'm doing on the both of the lambdas at the same time?
Ah, yes, that you can do. That you can do. No, sorry, you will not be able to do that. Because the lambda I define with one upper index and one lower index. So you cannot, you say lambda mu prime mu, you cannot do it for lambda because this is meaningless. Say I want to write that. That is meaningful. That I can do. Right? But it means that the inverse transformation, right? Okay, so sorry, that is something which is meaningful. This you can write. But something like that, this is meaningless because there is no such thing as lambda with 2 lower indices. This doesn't exist. Okay, so this explains why I use the term contravariant when I describe a vector. Because the component of the vector transform in the opposite way as the set of basis vectors. If omega belong to Tp star, is a dual vector, then it really is a map. In the linear sense, so then omega of A, V plus B, W, is A times omega of V plus B times omega of W, and this is real. Right, V and W are vectors, A and B are scalars. Now we can play the same game that we played previously, right? We can introduce a basis for this dual vector space. So a basis will denote by theta, basis for the dual vector space. I'm going to call it theta with nu. So the requirements for these vectors to form a basis is what? Is theta nu. This is a vector, right? It's a member of the dual space. So it can operate on a vector on the real space. So let's take a vector from the real space, right? So we call it, let's take the basis vector. So it operates on E, right, of mu. Give us what? Again, this is a vector, a basis vector of TP. This is a basis vector of TP star. So an element in TP star, right? Give it delta, exactly. Will give us a number. And the number is just delta of mu nu, correct? Okay, you all see that? If omega is an element in the dual vector space, then it's linear functional, basically, right? It just takes a vector and produce a real number in a linear way.
And I can write the delta with opposite indices from bottom because it's a delta function?
In principle, you can, but you just confuse yourself. Right, this is just a real number. And this is a basis vector of the space TP. This is a basis vector of the space TP prime, TP star, sorry. And so if it operates on a vector here, I get a delta function. Right? So any regular to the normal vector space, like any element in TP star, right? Any vector here, I can write in terms of its components in the basis theta, right? So again, any vector omega which belongs to TP star, to the dual space, right? I can write using its components, but now I'm going to label them with lower indices. So omega, I write as omega mu, theta mu. This is the component, and this is the basis vector of the dual space. So any vector omega, these are known as covariant vectors. Known as covariant vectors. Another name actually is known as one-forms, if you have heard of that. I don't know, last year I didn't have time to go through the P-forms theory, but I don't know if I have time. Depends a little bit on me and a little bit on you. If you want to go through the theory of P-forms. This is it's called a one-form. Also, another name is one-form, which you may encounter. So if I use the components, I have a very simple way of writing the action of a dual vector on a vector. Right? So let's write it down. So the action of a dual vector, or one form, on a vector, omega, that works on V, right, is just omega mu V nu, theta, this is the vector, right, mu, that operates on E nu. These are just numbers, so I can take them all out, right? So this is just omega mu V nu delta mu nu. So this is just omega mu V mu, which is a number, real number. So that's why we don't really use these, basis vectors. If we have the components, that's enough. We know everything we need to know. There's no real need to write down explicitly the basis vectors. Of course, using that, we can think of vectors as linear mapping from the dual vectors to the real numbers, right? So I can think of V that operates on omega. I'll simply define this omega that operates on V. Like just omega mu, V mu. So vectors are linear mappings. Of one forms to R. Again, vector is the 4 vector that I'm normally referring to. Contravariant vectors. I told you I'm going to use these terms exchangeably throughout this course. Let's see. So the dual space to the dual vector space is the vector space itself, obviously. Of course, the transformation of the dual vectors will be described in a similar way to the transformation laws of the vectors. So the transformation law of the components of omega, right? Of course, it's the inverse transformation. Omega mu prime is just lambda mu prime nu, omega nu. And for the basis of the dual vectors, theta rho prime is just lambda rho prime sigma theta sigma. So the components transformed by the inverse transformation, which is exactly what we'd expect to be. So a few examples, since this can be quite confusing. Hopefully the example I gave you makes things a little bit less confusing. So examples. So a few examples you know of, right? So the basic and most simple example is to think of vectors as column vectors. So V, I just write as V1, V2, Vn. And then what would be the one forms? It will be row vectors, exactly. Omega, so it will be omega 1, omega n. Right? And then omega operating on V is simple multiplication. To be careful, because I can also have V that operating on omega, but I already defined that. So that's well defined. Right. Second example, in quantum mechanics, what do you have? In Dirac notation? Bracket, exactly. You can represent vectors as cats, like V. And one forms would be the brass. And the action of one form on a vector, just a bracket, right? Of course, this is in quantum mechanics, this is a C number, right? It's not a real number. C, not a real number, but the idea is exactly the same idea. The third example, which I promised you, of the one form. something that transforms the same way as the coordinates, not the opposite, would be gradient of a scalar function phi. What is that? That's a set of partial derivatives to space-time, right? What is that? It's d phi over dx mu.
Your notation.
Right?
You should do d phi
dx mu.
because
By phi dx.
this is the differential, this is not the gradient.
This is how I'm going to describe the gradient from that one. Right, it's d phi over dx mu, right? I take the function and I derive it with x mu, right? Now we can use the chain rule to look at the transformation law. Right, d phi over dx mu prime using the chain rule. Right, I can write it as dx mu over dx prime d phi dx mu this is the opposite Lorentz transformation, so it's lambda mu prime mu d phi over dx mu. Now, because this is a dual vector, I'm going to use a new notation, which again I might just use it automatically throughout the course, so you need to know it. So d phi over dx mu, right, is going to be written as d mu phi. That's what it means. And this is the definition. When you see d mu phi, that means d phi over dx mu. And another very useful notation is just phi, comma, mu. So this is a notation. When you see that, that means d phi over dx mu.
Can you explain again why derivatives are called vectors?
Yes. In fact, the easiest maybe to see that, let me just write it down and then I will, if that is not clear, then I will explain it again. Let me erase this part, because I don't want to switch it. What happens when I operate a gradient on a vector? Right. So if I operate a gradient, which is one form, on a vector, v mu d mu, did I define the vector? I define it, right, along a curve, right? So I had some space, right, or manifold. I put a curve along that manifold. By the curve by lambda, so I know where I am. This will be lambda equal to 0, lambda equal to 1, this is lambda equal to something, right? At each point P, right, lambda got some value along this curve, right? And I specify the vector, right? There are these bases, right? Coordinates here, bases. Then there is a vector, different color, right? Use a vector V. Right? For V mu, right, the component of V, right, was just dx mu over d lambda. Now, so the operation of a gradient d phi on a vector, right, just d mu phi, d mu phi, right, dx mu over d lambda. Right, this is just d phi over d lambda. Using the chain rule. Now, I said that a vector is any quantity whose components transform in the same way as the components of the coordinates. Right? So x mu changes.
Opposite way.
A vector, which is a contravariant vector, is transforming. Its components transform the same way when the coordinates transform. When I change x mu to x mu prime, so would be the coordinates of v, components of v. That was my definition. Go back to your note. Now, when I change the coordinates, right, I did not change lambda. So this is clear why it was changing the same way as x changed. But the gradient phi over x mu. When I changed x mu, phi did not change. So gradient change according to the inverse distribution. Because now x is in the that you review the material at home, make sure that everything is clear in your mind. Okay, and this is simply a scalar, like d phi over d lambda. It's independent on the coordinate when I change the coordinates. All right. Questions so far? No? That means everything is clear? Should be, but I wouldn't put money that everything is clear to anyone at this point. Next week you will get the problem set so you can start practicing these things yourself. Right? Which again, I strongly urge you right now. Lecture number 3. You're seeing you better practice. Make sure that everything is clear in your head. Okay, but the nice thing about that, and you'll see that already on Sunday, we're working hard on the math, but once we finish, and we're pretty close to finish this part, I told you there are 2 parts, so we're pretty close to finish this part, then the physics will get out like that. We don't have to work it out, to just follow immediately. we're working hard on the math, but the physics will just be straightforward. You do nothing and we get the physics. Okay. But since we have a few more minutes, there is a very easy or straightforward way of generalizing these concepts of dual vectors. So I wrote down, no, maybe I should erase that. I wrote down that a dual vector I view as a linear mapping from vectors to R, right, to the space R. Now, I can generalize it in a straightforward way to the concept of tensor. How will I define a tensor?
Probably a linear map to vector space.
Nearly, it's just a generalization. So, since a dual vector is a linear mapping from the vector space V to R, I'm going to define a vector type or rank. Is a multilinear mapping from a collection of k dual vectors. Again, just to make sure that you're all with me, right? Dual vectors meaning one forms. This is all meaning the same thing, right? So k dual vectors and L vectors. Vectors means contravariant vectors, etc.
Why do
in general relativity we work in R? We don't need a complex. It's complicated enough. We don't need to further complicate. So when I say multilinear, it means linear in each of them. So how do I describe a scalar?
is the action of
It will be a what?
an action?
No, it's not an action. It's a tensor of what rank? Right? 0, 0. Tensor. 0. Is a vector. Vector. The what? 0, 1. Very good. Tensor. just follow just like this. Simply follow the mathematical rules. I told you that this course is margin between math and physics. Could be more on the physics side, but as you can see, there's plenty. Do you have any further questions? Okay. If you don't have any further questions, I think it's about time that we can say if we run out of time, or you want me to continue on. I don't mind. Right now there is no urge, and the fact that most of the meetings, as far as I know, possibly all of the meetings, international meetings for this semester are cancelled, means that there will be no losses of lectures this semester, so you may not be in a rush to continue more than needed. But we'll see how these things progress. So first I want to remind you, I'll see you then on Sunday at 10 a.m. This will be instead of lectures on Thursday, so we'll now shift to Sundays. So I'll see you on Sunday at 10 a.m. I do ask you, review this material. It's not difficult, but it could be tricky a little bit. It could be some new. There are a lot of subtle issues and delicate points, as I promised you. It's not too hard, but just make sure that you don't accumulate any gaps in your knowledge. Right? That you just make sure that everything is clear in your mind. And if you have questions, then please come and ask me, or send me an email. Anything else? No? The only last thing that I want to ask you is to talk to your colleagues. If there were more people, I think, or there are a few people that were here last week and are not here this week for some reason. So,
the seminar.
But
Because they have a solid state seminar.
I said, I think it was quite clearly last Thursday that we'll meet this Thursday and then we'll decide for the I cannot force anybody to be here. It's individual choice. Okay. Unless you have any further questions to me. No? See you on Sunday and have a great weekend.